All right, good afternoon, guys. We're going to start diving into frictional forces a little bit more concretely. We've dealt with it at a very basic level, and so we're going to dive into it a little bit more. What this will allow us to do is as we go into our energy unit, we're going to start to talk about dissipative energies, energies that sort of leave the system and that we can no longer get back. And we started to sort of play around with this idea a little bit on Friday. Frictional forces are what are responsible for those energies that are dissipated and that we can't get back. And so it makes sense that now we should dive into friction a little bit more and try to understand it at a deeper level. And so that's what we're going to do in this next video. Hopefully in the next 10 minutes you'll feel like you have a better understanding of friction, and of course through practice feel comfortable with it. And so we're going to start with the basic definition, which I think you're familiar with. The resistive force is what friction is. It resists motion, both for objects that haven't yet started to move and for objects that are already moving, also measured in newtons because it's a force. We haven't yet talked about the types of frictional forces, but we'll define them now. There are static frictional forces, and there are kinetic frictional forces. Static's a word that in sort of everyday language usage, I think people most commonly would say, oh, static is electricity. There's definitely a relationship there to what static actually means. I like to think about it in terms of English class, where we analyze characters through a novel. You have static characters and dynamic characters, static characters being the ones that do not change during the course of the novel. Static in physics as a term means that an object's not moving, it's not changing its position. And so for us, static friction is what occurs when the two objects that are in contact with one another do not move with respect to one another. And so the good example to think about here would be, let's say you wanted to move your refrigerator at your house. You go next to it, you start to push on it, but you realize you can't move it, you can't apply enough force to overcome the friction between it and the floor. You're applying the force in one direction, there's a resistive force of friction, that static friction that is keeping you from moving the refrigerator. And so in terms of directionality, static friction is parallel to the contact surface, which we already knew, but it's also opposite the direction of the net force. So whichever way you're pushing or applying a force on it, the resistance is in the opposite direction. Kinetic friction would be what would happen if you started to get that refrigerator to move. So you're pushing on the refrigerator, and then all of a sudden it starts to move, and you keep moving it. You're still feeling a resistive force to the motion of that object, and therefore there's still some friction, and we would call that kinetic friction. In other words, the two objects are sliding across one another. Also parallel to the contact surface and opposite the direction of motion this time. So it doesn't have to be opposite the direction of the force, it's just opposite the direction that the object is moving. It's helpful to kind of visualize this in terms of a graph. And so this is a graph that I'll explain very briefly. It is a graph of the applied force. So you might think about this as the force that's applied to the refrigerator. And that force applied is being plotted against the net force, or sorry, not the net force, the force of friction. And so let's see what happens in this graph. And let's keep our refrigerator example in mind, because it's an easy example to think about. So you start to apply a force on your refrigerator, trying to move it. And for a while, you apply a force greater and greater and greater, and it's not moving the refrigerator. And that's because the frictional force is equaling out or balancing that applied force. And that's why you see a linear function right here. It's a one-to-one function in that the same applied force that you are applying here is balanced by an exact same frictional force. And it's not until we get out of this static region, which we can label, this is the static region here. Once we get up to this point, that we reach the maximum force you can apply before the object starts to move. And so maximum applied force gives you this maximum frictional force. We call this the threshold of motion. Because at this point, once you overcome this highest peak, you notice there's a sudden drop, and then there's a leveling out of the graph, a horizontal line that follows, and that's the region where we start to see the object move, and it experiences kinetic friction at this point. And one thing you'll notice about kinetic friction is that it is the same value all the way through. And so the two key things to keep in mind here is that we can apply the static frictional force. It will be greater than its maximum value. It will be greater than the kinetic friction that occurs after the object starts to move. This also suggests why it's easier to keep objects moving than it is to get them started moving, because of that difference in the two types of frictional forces. Let's talk a little bit more specifically now about the equation that guides how this frictional force works. So there's a couple things we're going to consider. The first thing we want to consider is it does depend on the surface. So obviously, if you are driving out on the road and there's a lot of ice on the road versus a dry road, you have different levels of friction occurring there. There's a lot less friction between you and the road if there's ice than there is between a regular dry asphalt road. And so the surface obviously matters here, and the question is, how does it matter? Well, in our equation there's going to be a coefficient that looks like this. It's the Greek letter mu. It looks like a U that has longer sides on each side. So it's pronounced mu, just like muma. And this is the coefficient of friction. And this number will tell us about how much friction is between the two surfaces we're looking at. It's obviously unique for different surfaces. For example, a tennis shoe and the basketball court floor is a different frictional surface than between a tennis shoe and, say, the tile floors in the school, or a tennis shoe and the rubber floor that's in the cafeteria, or your rubber shoe versus the concrete outside. Like, those are all different surfaces and all would have different mu's to describe what that friction is like. So it matters on what the surfaces are that will affect the friction. The other thing that's going to matter is the normal force, F sub n. In that the greater, we could say the greater F sub n, we can conclude that the greater the frictional force. This is easy to see if you take an object on a flat plane surface and you increase its mass greater and greater and greater, that object becomes harder and harder to overcome its friction before you get it moving. And so this is something we've all experienced in our lives. And the equation then comes out to be the following. The frictional force, F sub F, is less than or equal to mu times the normal force. So this coefficient will guide how much of the friction of the normal force causes us to have a frictional force. Now you notice this less than or equal to sign might be a little confusing, but if you come back up here to the graph, you'll see why. The less than or equal to part refers to this entire piece where at any point the frictional force could be less than this highest peak, depending on what the applied force is. And so we have to keep that in mind. That's where this less than or equal to sign comes in. If we are at the maximum threshold, or if we were past that, then we go ahead and just say that they are equal. This is for the segment after that point. And so this is the equation that we're going to become familiar with over time in application. And so make sure that you have this specific equation down and we start to become familiar with it. I want to do one last thing in this video, which is to talk through a conceptual example that will help you think a little bit further about how the frictional force works. So the example is over here on the left side. What I want you to imagine is the following. So I have a surface here with two masses. Each mass has the same value of mass. So m is equal to m. We're going to think about object 1 and we're going to think about object 2. And there's one other claim I'd like to make, and that is that mu is the same for each surface. And so I want to look at the effect of pushing on these two surfaces in two different ways. So let's consider this first scenario. The first scenario here, I'm pushing with a force F horizontally on our mass, and we would ask the question, well, what frictional force would it feel? Well, we'll start with the force diagram here. What I would instantly see are that Fn is balanced with mg going down, and that there is a force F pushed to the right, which means that there is a frictional force balancing that. If we want to say that, let's go ahead and say that these are static cases, so these are not objects that are moving. And so I get a balanced scenario, and we can see that there's this relationship between the different values. That relationship is centered in this equation. The normal force here times whatever the coefficient is between these surfaces will give us what the force of friction is. And that determines how hard we need to push before we can get this object started to accelerate. Let's consider this different scenario though. Let's pretend now I don't push horizontally, but what I do is I push at an angle down towards the object. Same force, but now I'm pushing down into an angle. Well, let's ask the question, what's happening here? Well, if I were looking at the force diagram, I would still have mg, and it would be the same going down, but I'd also now have a I would